Hello, everyone. Good morning. First, I want to make an announcement about the final exams. The final exam will cover up to section 5.4, which we are going to start today. I will give you the final exam problem next week and let you know when it's due. For the final exams, it's open book and you can use my lecture note. Other than that, there is no special requirement. Okay, so today we do section 5.4, some theorem. On Ito's formula. More generally, we have the following theorem. On generalization of Ito's lemma, Ito's formula. Given in the previous section. Okay, so the first theorem is suppose we have a function theta of t and x and y. And now, if we put x sub t, y sub t, with x sub t, y sub t, the same thing as given in section 5.3, then what is the stochastic differential? Well, obviously, you see, we have for the dependence of theta on t, which is within Newton's calculus. And so the stochastic differential of this is given by theta sub t dt. We have this actual term. Then in the Ito formula from the previous section. And that is given by okay, maybe I write it this way. Okay, that equals to theta sub t. And here this we should have x sub t, y sub t, but let's not worry about it. It's just to make it easier to read, dt. And then we have theta sub x dx sub t, and then plus 1/2 of theta sub x, and then dx sub t squared. This is for x sub t. And for y sub t, we have plus theta sub y dy sub t. And then here the critical thing, minus 1/2 theta y sub y dy sub t squared. And we can write it in the stochastic integral form, which is a little bit complicated, but it's enough just to state the theorem this way. Okay, another theorem is this time theta depends on t and also depends on x and y here. But I'm sorry, depends on t, but there are several x and several y's. Namely, there are several equal processes x sub t, the first one I put sub 1 here. And the second one, x sub t 2. This is the second equal process. And x sub t, say we have for n of them. Okay. And then we have several stochastic processes in the counterpart, which I denote by y sub t, but sub 1. All the way, well, maybe I write one more time. One more y sub t sub 2. There's a 2, and y sub t sub, say, m of them. What is the stochastic differential of the composition of theta with those stochastic processes and also t? Well, it's easy to write it down. It's theta sub t dt. First, for the variable t, we have this term. And now, for the equal processes, we have the summation I from 1 to n. And theta sub the partial derivative with respect to x sub I. And then dx sub t sub I. And then we have 1/2 of summation I j from 1 to n. And this is theta sub x sub I, x sub j, dx sub t I times dx sub t j. So this is for the equal processes. Now for those stochastic processes in the counterpart, we have plus summation. Since I use ij, so I use k from 1 to m. And theta sub y sub k and dy sub t sub k. And then minus 1/2 summation kl from 1 to m of theta sub y sub k sub y sub l. And then this is dy sub t k dy sub t sub L. Okay, so this is the more general Ito formula. And of course, this is in terms of stochastic differential, and real meaning of this stochastic differential should be written as the stochastic integral, which is easy to do, but rather complicated to write it down. Okay, so let's turn to the next page. This is page 50. Okay, now I'm going to give you one interesting examples. Okay. Let's find out the stochastic differential of theta, bt, and b1. So here we have b1 here as the second part of theta. If b1 were not there, this would be within Ito theorem. But now with b1 there, let's see what happened. First, let me mention that this is given by RU and K in 2008. With different using, I'm sorry, okay. Using a different method. I will make some further remark about this later on. Okay, so how do we find out the stochastic differential of theta bt b1? We are going to use the second theorem in the previous page. Namely, this b1 is decomposed into two parts, bt plus b1 minus bt, which we are familiar now. This has been used several times. This is the Ito part, and this is the counterpart. Therefore, you see theta bt b1 equals to theta of bt, and b1 is decomposed into bt plus b1 minus bt. This. And note that here we have BT is the equal part, and this is the counterpart. So you see here we have one stochastic process BT, and another one in the counterpart B1 minus BT. So we can put the x sub t equal to, okay, so here put x sub t equal to BT, and y sub t as B1 minus BT. So you see we have one little process and another one in the counterpart. And then we define a function. Define a function f of x and y equals to, let's see, this is theta of x plus y. Then the reason I define f this way is so that f of x sub t y sub t. This is f of x sub t. This is what? This is theta of x, theta of, oh, I'm sorry, okay, let's see, theta of x. This x is for BT. And then x plus y is BT is for xt plus y sub t is B1 minus BT. Which is theta of BT. And then this is B1. And so this is f of xy equal to that. Therefore, hence, theta, the stochastic differential of theta is the stochastic differential of f of x sub t y sub t. So we need to find out this equal to what? This video is a little bit too long, so we'll next time. This will to find out this question mark in the next video. Okay, so take a break.